We are going to talk about and use 5 basic rules of exponents. Please have your table ready if you do have that handout given to you prior to these notes so you can fill in the information in an organized fashion. The first rule we'll look at is the negative exponent rule. The negative exponent rule is exactly how it sounds. The situation is that you have a base that's got a negative exponent. Normally in mathematics, a negative exponent is not considered a fully simplified value. So to fix the exponent, we reciprocal the base that has a negative exponent to the other side of the fraction bar. So in the situation where you're given a monomial or a term that is not looking like a fraction, it's easiest to view it as a fraction. So I'll put the whole term over 1. Right now, 4 has a power of 1, which is not the issue. X has a power of -3, which is the issue. It needs to be simplified. So the fix again is to take the base x and move it to the other side of the fraction bar. The 4 is going to stay above the fraction bar because its power of 1 is fine. It's the base x that needs to move to the bottom, and now the power becomes positive. That flipping over from the above the fraction bar to below automatically makes the negative sign disappear and become a positive power. Another example here, 2y over another monomial, 3x to the -5. We've got 1, 2, 3, 4 different bases. This has a power of 1, this has a power of 1, the 3 has a power of 1, but it's the x that's got a negative exponent, and so that's the only thing that really needs fixing. And to fix it, it's going to move to the top, the opposite side of the fraction bar. So it's below now, it's going to move to the top to get fixed. So we'll have 2y x to the +5 because moving that base changes the sign on the power. And of course notice everything else doesn't move. The 2 stays, the y stays, the 3 stays, and usually you might see the variables lined up alphabetically. So I'm going to rewrite this here as 2x to the 5th y, since x comes before y. The second rule we'll look at is called the product rule, and it happens when bases that are the same are multiplying together. The rule says what you can do as a shortcut is add the exponents. So in this example here, we've got 2 monomials being multiplied together, but what is really happening is that your x's, this x is multiplying to this x, this y is multiplying to that y. In reality, when you're multiplying, you can actually jumble all kinds of stuff. So this is the same here as saying x squared times x to the 4th times y to the 7th times y to the 1. I'll put the power there. And so when you do the shortcut, the rule here says you add the powers for the bases that are the same. So this becomes x to the 6th here, 2 plus 4, and then the y's with the same bases, those powers add up. You get y to the 8th. Now keep in mind really quickly here, if I was to do the expansion because I don't know the shortcut by heart, this here would be saying x times x for x squared times x, 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 x for x to the 4th. And as you can see here, we've got 1, 2, 3, 4, 5, 6 x to the 6th. Same thing for the y's. If I don't know the shortcut, I can always expand. 1, 2, 3, 4, 5, 6, 7 times another y to the 1, and that's where we get the 8 for the power on the y. The third rule we'll look at is the quotient rule. Quotient means division. So when the same bases are dividing, like x divided by x, y divided by y, the shortcut says you subtract the bottom exponent from the top and then adjust any negative exponents if that happens as a second step. So applying this rule here, I'm focusing on the bases that are alike, so the x and x, and then the y and y, and the rule says you subtract. So the bottom power from the top. So here I'd be calculating 8 minus 3 for the powers to get 5. And what that does is that actually brings this base up into the top base. So you don't have the x on the bottom anymore. Same thing with the y's. I'll have y 2 minus 3 is actually negative 1. And at the moment, all I've got is 1 in the denominator because, again, the rule actually brings all the y's to the top, all the x's to the top. At this point, though, I notice, uh-oh, that y is not simplified because the power is negative. So I've got to do one more step, and I've got to do the negative exponent rule, which takes the y and puts it back to the bottom where its power is going to become positive. So x to the 5th over y to the positive 1. Again, the quotient rule is a shortcut to the expansion version, so if you can't remember the shortcut, you should try to do the expansion method, which actually has you write out all the powers in expansion form. So here's x to the 8th, here's y squared, here's x to the 3rd, and y to the 3rd on the bottom. So with the expansion, what you can do then is cancel 1 for 1 match on the bottom, and numerator to the denominator. So here an x would cancel an x, this x, that x, this x, that x, and then there's no more canceling for x. You've got this left over, x to the 1, 2, 3, 4, 5. That's where we get x to the 5th. Then you would do the same for y. Cancel a y at the bottom. This y goes with this y. And then notice what we have left is a y to the 1 on the bottom. So actually the expansion tells you a little bit faster where you're going to have something left over, which is that y that's left on the bottom there. Our rule actually brought the leftover y to the top, which then we had to bring back to the bottom when we did the subtraction of the powers. So either way is fine, but if you can remember the quotient rule, sometimes you can visualize the expansion in your head, which also works. The rule power to a power is exactly that. It means you've got some powers that are being raised to another power, and when that happens, it'll always be this parenthesis visual here, parenthesis with something inside with has a power, and an outside power on the outside of the parentheses. So when bases with exponents getting raised to a second exponent, that's what we mean by the parentheses with a power on the outside. It's called getting raised to a power. The exponents multiply. So this 4 here multiplies to the powers inside the parenthesis. So this 4 here multiplies to the 3 to get x to the 12th. And then it also multiplies to the 6 for the other power for y to get 24. Really quickly, in the expansion form of what's going on here, the 4th power out here is saying we've got 4 of these groups here. 1, 2, 3, 4 of those multiplying together. Then when you kind of break that down, each of these, you've got an x to the 3rd, which is an x times x times x. You got a y to the 6th, which is y, 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 y. So if you picture how many of these do you have, x to the 3rd, you've got 1, 2, 3, 4. So 4 times 3 is 12, and that's where we get x to the 12th. You got 6 y's here. 1, 2, 3, 4 of those. So 4 times 6 is 24. So that's quickly a quick view of the expansion explanation of this power to a power. We're at our final rule, power of 0. This is an interesting rule. The situation is that we have a base or bases that have an exponent of 0. So x to the 0, sometimes we have a group going to the 0 power. Pay attention to that. The base cancels to 1 completely. So here at x to the 0, this outcome is just 1. Okay, keep in mind, x to the 1 is x. X to the 0 is 1. That's different than saying 1x. Another example, here is 4 times a group to the 0 power. Please recognize that 4 is a base that has a power of 1. It has nothing to do with that power of 0 because it's not in the parentheses. But what's in the parentheses is all going to the 0 power. So what happens here is that this is 4 times 1, because this whole group cancels out to 1, and you're left with just 4. If we were to apply some of our other rules that we've used, like the power to a power, the one that we just talked about, this could, if you wanted to take that step, first become x to the 0, y to the 0, as you multiply 2 times 0 and 6 times 0. Then this becomes 1. The y becomes 1, and you end up with 4 times 1 times 1, which still comes out to 4. So the power of 0, very interesting power. If you have a calculator, you can actually test to see how correct I am on that. You can do the y to the x button on your calculator, and then you can put in any base for y. Some of you have a button that looks like that, like this, with a caret symbol. Okay, so try putting in, if you want, not a variable but a number, 6 to the power of 0. So put in your base of 6 and put in 0 for your power, and sure enough, you should get 1 as your result. Please make sure you jot down these hints here on simplifying. We're going to do some examples together to see this in action here, but this is just applying the orders of operations. So following PEMDAS, here are some hints. Always work on the innermost of parentheses first, and that's why P is there first in the list of orders of operations. E is your exponent, so that would be like your power to a power. Multiplying and division are interchangeable, whichever comes first, left to right. So you could be applying the product rule, you could be applying the quotient rule. Remember to multiply coefficients and use a product rule for powers. Or you can always fall back to expansion if you don't know, if you can't memorize your rules. Monomials that are dividing, usually you reduce your coefficients. And of course the quotient rule for subtracting the bottom power from the top. You're never allowed to have decimals when we're doing our simplifying problems in this unit. So keep in mind that if you've got decimals if you end up with decimals as a result, you need to back up. Decimals are not allowed. Negative exponent, that rule there should be saved for one of the very last things to do, because sometimes negative exponents will rule itself out in the middle of doing other rules. And again, if the rules are hard to remember and you can't recognize the situation when to apply, you can always expand. That just means you might take a little bit longer to complete something in comparison to someone who's going to be able to use the rules by memory. All right, let's see if we'll have fun doing these in class.